right, everyone. It's about 5:30, so it's time to go ahead and get started, even though there's no one here. So we're going to start off in chapter 5. We actually, the last time we met, we finished with example 5.8. So I'm going to jump into example 5.9 and go ahead and knock out chapter 5. I may or may not be able to start into chapter 6, but either way, it'll be here, and it'll cover the air resistance portion because I was unable to get to that last night in my PHY 241 N02 class. So hopefully they'll be able to refer to the end of this video to get that at least. So we're going to start off by sharing my screen. Normally we would start off, of course, with me asking if anybody had any questions, but there's nobody here, so I can't ask if anybody has any questions. So we're just going to start off with example 5.9, which I'll be reading in a second, and I've already written it up in my iPad. So hopefully the iPad screen will come visible now. So you see example 5.9. I've gotten the data that they gave me as well as the solution equations that I'll be needing. I won't necessarily need F equals 1 over T. I just want to remind you of that. But here's example 5.9 called Moon's centripetal acceleration. The Moon's nearly circular orbit about the Earth has a radius of about 384,000 kilometers and a period of t equal 27.3 days. Determine the acceleration of the moon toward the Earth. That's the centripetal acceleration. Remember, centripetal means center seeking. So it's an acceleration towards the center of the circle, and it's actually in the same plane as the circle. So keep that in mind. That's part of the reason we did that derivation, where we used r equals r cosine omega t plus I hat plus r sine omega t j hat. And taking the derivative gave us velocity, taking the second derivative gave us the acceleration, and then when we calculated the magnitude, we got omega squared r, which also was equal to v squared over r. So in order for us to do this, we can't use the 27.3 days in days, so I've already converted it to seconds, and you can see I multiply by 24 hours per 1 day. And then I multiply by 3,600 seconds per 1 hour. The days cancel out, the hours cancel out, and we get seconds, and it's 2.359 times 10 to the 6th seconds. So 2,359,000 seconds is roughly how long 27.3 days is. Additionally, the 384,000 kilometers would be 3.84 times 10 to the 5th kilometers, but we want it in meters, so it's 3.84 times 10 to the 8th meters. That might also help you to remember this because it's a little bit bigger than the speed of light. Remember, the speed of light is 3 times 10 to the 8th meters per second to 2 sig figs, more or less to 3 sig figs. And because of that, you can see that this is a little bit bigger than 3 times 10 to the 8th meters, and therefore it takes about 1.2, 1.25, something like that, seconds for the light that hits the surface of the moon and to bounce back and hit us. It takes, like I said, about 1.25 seconds. So anyways, we are asked to determine the centripetal acceleration, and the formula for centripetal acceleration that we derived was omega squared r, and then I used v equals r omega to convert that to v squared over r. We also know that when something travels at a constant speed in a circle, then since it's the constant speed, the average speed is the same thing as the speed, and that is distance divided by time. And of course, the distance around a circle is considered to be the distance around the circle is considered to be the circumference, and then the time required for it to complete one trip around the center is called the period of, in this case, revolution, because it's the period of rotation, which would be the time required for this to go like that to that same spot. So that's rotating about an axis that goes through the body. However, if you wanted this to orbit, then the time required for it to go from here to here again, that's the period of revolution. And then, of course, if it was a pendulum, the time required for it to go from here back to here is the period of oscillation. So that's the three scenarios in which t is a period. And of course, the period and the frequency are related by the frequency is equal to 1 over the period. The frequency is what we measure in cycles per second, or something like that. A cycle and a revolution is more or less the same thing. So a cycle per second or a revolution per second. They also use units of CPS that you might see in some older manuals, or the most modern use of the frequency is a unit called the Hertz, capital H, lowercase z, named after Heinrich Hertz, who you'll learn about in the electricity and magnetism portion, i.e. Physics 242. So let's go ahead and work this out. We know, for instance, the period, that's the time required for it to complete one revolution. We know the radius, so we can go ahead and calculate, excuse me, we can go ahead and calculate the velocity given 2 pi r over t is that velocity. That becomes 2 times pi times 3.84 times 10 to the 8th meters divided by the period, and the period turned out to be 2.359 times 10 to the 6th seconds. So when I do this math, I'm going to multiply 2 times 3.14159 times 3.84 times 10, excuse me, times 10. Ooh, my pushing of the times 10 did not work. So 3.84 times 10 to the 8th. Let me read what I just typed in. 2 times 3.14159 times 3.84 times 10 to the 8th divided by and sometimes it's just best to use parentheses around it. It's not supposed to be required to use parentheses around this, but I did discover one time that a calculator did this to me, and I might have imagined it. All I know is it messed me up, so I don't trust it anymore. So after the division symbol, I put parenthesis, and then I type in 2.359 times 10 to the 6, and then close parentheses. What actually happened that time was it took the 2.359, say, and divided that, but then it took the times 10 to the 6 and multiplied that by the answer. So it's like it took the 10.6 up top, or the 10 to the 6th up top, and it took the 2.359, called the mantissa, in the bottom. So I've constantly lived in fear ever since that happened that one time. I'm hoping I imagined it, but I was using another person's calculator. So anyways, I just don't trust it anymore. When I do that calculation, I get 1,023, and that is in meters per second. So uh, that's roughly 2,000 miles per hour if you want to know it in miles per hour. But that gives you an idea that the moon is actually moving pretty fast in the night sky. Actually, in the day sky too. So now that we have the velocity, we can go ahead and calculate the centripetal acceleration. The centripetal acceleration is v squared over r. So I'm going to take that 1,023 meters per second. I'm going to square it, and then I'm going to divide it by r, which is 3.84 times 10 to the 8th meters. And doing that, I get 1023 squared divided by parentheses 3.84 times 10 to the 8th, close parentheses, and that gives me actually it gives me 0.002725 meters per second. And someone just tried to come in, so I'm going to go ahead and admit them. So that is the centripetal acceleration of the moon. In fact, that's a pretty famous historical event. Specifically, Newton, when he came up with his idea of what the force of gravity looked like, he actually used that to calculate what the force of on the moon would be, and from that he was able to calculate the acceleration the moon would have to have, and lo and behold, he got the same result by using his law of gravity. So he, at that instant, was the only person on planet Earth that knew exactly why the moon orbits the Earth and why the Earth is able to orbit the sun, even though both of them have no physical attaching, for instance, the moon to the earth or the earth to the sun. So it's a kind of interesting and neat calculation. You'll see that we'll use that result in the next chapter as well. I didn't need quite as much space as I left, so I'm going to move this up a little bit by cutting it and then pasting it up there. I don't think I'll need this much room anyways, but better safe than sorry. So now I'm going to example 510. We have already saw figure 5.9, and it gives you a little bit more information. For instance, in the note, it tells you that that's 2.78 times 10 to the negative fourth g. So that's really a small fraction of g forces, and that's why you hear astronauts often say in microgravity. They'll call it microgravity as opposed to saying weightlessness or zero gravity. In fact, if you're orbiting the Earth, you're certainly not in zero gravity, because if you had zero gravity, then there would be no force to keep you in orbit around the Earth, just like there would be no force to keep the Earth and, or excuse me, to keep the Moon in orbit around the Earth, nor there would be any force to keep the Earth in orbit around the Sun. So if it really was zero gravity out there, uh, we wouldn't be able to have these circular orbits. Now, example 5.10, after it talks about centrifugation, is 5.10, the ultracentrifuge. The rotor of an ultracentrifuge rotates at 50,000 RPMs. I'm going to pretend that's 3 sig figs, even though it's clearly what your author would call ambiguous. Okay. But I do want to ask you, actually, I would normally ask the whole class, but I only have one student here. So, Christine, if you actually know, by all means, answer the question. That would be helpful to me. But if you don't feel bad. I'm not trying to pick on you. I'm just lucky to have a student here with me, so I'm happy about that. But anyways, can anybody tell me what variable you think you should assign the 50,000 revolutions per minute to? Is that like a velocity? Is that an omega? Is that a v? Is that a t? Or is that an f for frequency? That sort of thing. You have any idea, Christine? And you can speak up or type it in the chat, whichever one you do, whichever one you want. Looks like there you go. Is it R? So what we use, by the way, in trying to figure out what variables go with what, is we sort of look at the units. A lot of times, if you can't physically understand what the concept is, you look at the units. If it was R, it would be a radius, and that would be some kind of unit of length, like centimeters or meters. But this has units of revolutions per minute. And you weren't here when I previously explained this, so this might be part of the problem. But a revolution and a cycle are the same thing. So you might also call this 50,000 cycles per minute. When you think about it that way, then you'd probably understand that the quantity is the frequency f. So thank you for trying, Christine. Again, like I said, you had a little bit of a disadvantage because you hadn't heard me explain that a revolution is the same thing as a cycle. Remember, period is the amount of time it takes to complete one revolution or one cycle, whereas a frequency is the number of cycles or revolutions that happen every second. In this case, it's not every second, so it's not really that reasonable to think of it as F immediately, but when you realize the other alternative is, nothing. So the only choices are frequency, which would be cycles per second or revolutions per second, or angular frequency, which is the omega symbol, and that's measured in radians per second. It's clearly not radians. So you might argue that it's omega or F. Either one of those are in some sense correct arguments. It's just a matter of what the units are in. So we're not going to be able to use the 50,000 revolutions per minute. We're going to have to convert that to cycles per second or hertz. So let's go ahead and do that. Oh, by the way, it says the rotor of an ultracentrifuge rotates 50,000 RPMs, revolutions per minute. A particle in a test tube is 6 centimeters from the rotation axis. Calculate its centripetal acceleration in g. So we're going to calculate it straight up, and then what we're going to do is divide by g, and that will give us the acceleration, the centripetal acceleration in units of g, or what people often call g forces, even though it doesn't really make any sense to say g forces, because g forces are measured of accelerations in g's, whereas this is not a force. So, anyways, let's start off with the fact that we know for the solution we can use AC, which is either omega squared R or V squared over R. We know that. We also know, for instance, velocity is 2 pi r over t if it's traveling at a constant speed in a circle. We're not going to need that here, but I will need to convert this f. So f is equal to 5.00 times 10. Notice I told you I was going to make it 3 sig figs. That's me just doing that. So I'm going to call that 5.00 times 10 to the fourth. And that is revolutions, which is the same thing as cycles, but it's per minute instead of per second. So I'm going to say 1 minute is equal to 60 seconds, and then that will be equivalent to cycles per second, and that's also equivalent to hertz. So if I take 50,000 and divide it by 60, I get 8.33 times 10 to the 2, and that's hertz, capital H, lowercase z. So now we have the frequency in the appropriate measure. Of course, we also realize that the frequency is 1 over the period. So we can, in principle, figure out from that what that is. But we also know omega is equal to 2 pi times f. So in this case, it'd actually be smarter for us, instead of trying to work out v squared over r, it'd be smarter for us to use omega squared r. So that's what I'm going to do. So omega is equal to 2 pi times f. So I'll write 2 times pi times 8.333 times 10 to the 2 hertz. And that gives me 8.333 times 10 to the 2 times 2 times 3.14159 gives me 5.236 times 10 to the third, and that is now in radians per second, because you can look at that 2 pi as if it's 2 pi radians per cycle or 2 pi radians per revolution, either one. So now we have the omega, and AC, of course, is just omega squared r. So all we have to do is take the 5.2, oops, forgot to underline the non-significant figure, 236 times 10 to the third radians per second. That's going to be squared, and then times the radius, which is 6 centimeters, but we had to convert that to meters, so that'd be 0.0600 meters. Now, one thing you got to remember is the radian comes from that equation S equals R times theta, where theta has to be measured in radians. If you solve that for theta, you get S over R, which is the arc length divided by the radius. The arc length is usually measured like in meters, and then the radius, of course, would be measured in the same unit. So the radian is actually a pure number. It's not an actual unit. So you can add radians in a unit at any point, just stick it in there, multiplied by 1, or stick it in there multiplied by meter if you want to. And you can also just erase it. And that's what we're going to do here. We're just going to erase the radians. So I'm taking the 5.236 times 10 to the third, and I'm raising that to the 2 power. And that gives me 2.742 times 10 to the seventh. And now I'm multiplying that by 0.06. Oops, 0.06. Now when I multiply that, I get 1.645 times 10 to the sixth, and that's in meters per second, because remember, we squared the radians per second. The radians we can just erase. That means we get per second squared as the units, but then we multiply that by meters, so we get meters per second, or meters per second squared. So that's it, but we want it in G's, so A sub C in G's is equal to 1.645 times 10 to the sixth meters per second divided by G, which is 9.80 meters per second times G. And now you can see why it works this way, because all I did was multiply by G over G. And if you multiply by G over G, you're multiplying by 1, so you don't change its value. So I'm going to take this 1.645 times 10 to the sixth and divide it by 9.80. And that gives me 1.679. Oops. That gives me 1.67. I'm sorry, that 6 is really getting ugly there. So 1.679 times 10 to the fifth G's is the actual acceleration. And that's the answer. you can see that's literally on the order of 100,000 Gs. And just for the record, Gs are things that we have to experience, for instance, during acceleration, like astronauts deal with that in taking off from Earth. They deal with that to some extent, potentially in re-entry. That all depends on how it's done, stuff of that sort. But that's a particular taxing situation for the human body. So that's one of the uses of the centrifuge is you can make a big centrifuge and allow actual astronauts or pilots in that centrifuge so they can experience the high Gs and teach themselves how to deal with those high Gs. So, for instance, if you do a turn in a jet where you're going like this, then your head is pointing up and you're rotating this way. So all of your blood in your body is attempting to obey Newton's first law of motion, which means it's trying to go that straight distance it was originally going, but now you've shot up. So all the blood appears to be going down toward your feet. If that's the case, that means you're not getting as much blood to your brain and you could literally pass out. So pilots often wear these suits that actually help them. They're sort of, they look like they're sort of elastic or extremely tight so that they can use that to hold the blood where it is. Plus, they do sort of like a Valsalva type maneuver where they're forcing the pressure to get really high in their head, and that keeps the blood up at the top. But they couldn't practice things like that in a safe situation if it wasn't for centrifuge. Another thing we use centrifuges for is you, for instance, know right now Iran's in the news, and that's specifically in the news about nuclear weapons. So it turns out nuclear material, uranium-238, is what naturally occurs in nature, and about 99.3% of the uranium you find on planet Earth is uranium-238. That means the other 0.6% is the other isotopes, and the one that we need for nuclear fission, for power plants, or nuclear fusion, or fission for nuclear weapons is uranium-235. So if we make a very complex centrifuge, we can actually separate out the uranium-238, which is obviously heavier than the uranium-235. And by separating it out, we can make what's called enriched uranium. So we can take uranium that's 99.3 uranium-238, and we can, get it up to 5% or 3%, which is roughly what you got to get as a bare minimum. 3 to 20% is what you need. They actually can do it even with not enriched to make a power plant, but it's not a very efficient power plant. Better, more efficient power plant generally is from 3% to 20% enriched uranium. However, if you want a weapon, you need greater than 80% enriched uranium. So that's another use of centrifuges. Any questions on that before we move along? All right, so that was example 510, and now we're going to section 5.3, which is called dynamics of uniform circular motion. And the first example we're going to encounter here is I should point out that example or figure 516 is trying to point out something to you that really, really is the crux of this matter. I've been looking for a video I saw on Twitter one time. It was a wonderful little pie plate that someone had, and they took it and they were spinning it like this, or wobbling it like this with a ball in it. So the ball was going around in a circle. And what they had done is they took that pie tin and they cut out a 90-degree segment of it from the very center, like a pie piece that was literally a quarter of a pie. And while the ball was rotating around like this, but it wasn't in the separated pie piece that had been cut, they pulled that piece out. And what you see is the ball goes around the curve and then it gets to that opening and it goes straight out. It doesn't shoot radially outward, which is what figure 516 is trying to show you. When we think, for instance, we're riding in a car and someone takes a hard left turn and we're in the passenger side, it feels like we're getting slammed sideways up against the passenger side window. But in reality, all that's happening is as the car is turning this way, we're trying to keep going straight forward, and that just feels like it's being pushed outward. It's still just actually trying to go straight ahead. So it's really important to understand that that's really what happens. It obeys Newton's first law of motion, and pretty much what happens is the instant a string or whatever's being used to give it that centripetal acceleration, the instant you remove that centripetal acceleration, the object doesn't shoot radially outward. It just continues on whatever velocity direction it was going the instant that centripetal acceleration went to zero. So, right here, for instance, if it's rotating around this, right here at the bottom, the velocity's that way. Right here it's that way, right here it's that way, right here it's that way, right here it's that way. So when it's right beside it, the velocity's up. If you cut off the centripetal acceleration at that time, the object's going to keep going up instead of going out like this. That's the big thing you got to understand. So that's part of what you want to understand. And it also says that would be called something that makes it shoot outward instead of forward, would be called a centrifugal force, Centrifugal. It's often spelled funny ways and pronounced funny ways because people never write it down. But it's a fictional force. It's not a real force. There's no force that causes the thing to go straight ahead, nor is there any definitely no force that makes it to go center fleeing, which is centrifugal. That's what that means is center fleeing. There's nothing that makes something go center fleeing, and if it was, that would be called a centrifugal force. What really is the origin of the centrifugal force is when you use Newton's second law, the summation of the forces is equal to mass times acceleration. If you're calculating the acceleration in a rotating reference frame, you'll find that by using the chain rule and all that stuff, one of the derivatives ends up giving you a term that is center seeking. That's the centripetal acceleration. And if you inadvertently take that term, which is like negative on the MA side, and you pull it over to the positive side, then it becomes, I mean, to the summation of forces side, then it becomes positive, and therefore, instead of it being centripetal, it looks like it's centrifugal. But it's not a force, and it's not supposed to be on the left-hand side of Newton's second law. It's part of the acceleration. So we've just been stuck over years from just hearing and people misunderstanding physics by calling it a centrifugal force, when in fact the force necessary to keep something in a circular orbit is a centripetal force, and the centrifugal force is a fictional force or a fictional force. So let's jump to example 511, which is kind of a neat one. So here it is, example 511, force on a revolving force on a revolving ball. Remember, I differentiated revolving versus rotating last time or in the past a couple times, and I did it again today. So just keep that in mind. Revolving is when you're orbiting around some axis that's not within your body or within the body that's doing the orbiting. When you're rotating about an axis through the body, then that's normally called revolution. So, or excuse me, rotation. God, that was the worst thing ever. But anyways, so yeah, when it's rotating about an axis through the body, like dead center here, that's rotating. Okay. Even rotating like this is rotating. So that's rotation. But once the axis comes over here, then the thing is doing this. That's revolving. Okay. So keep that in mind. Now let's look at example 5.11, and it says estimate, and I'll follow up with a more precise calculation at the end for sort of extra, if you will. It says force on a revolving ball, parentheses horizontal. Estimate the first. Okay, so I can't read right now. Estimate the force a person must exert on a string attached to a 0.150 kilogram ball to make the ball revolve in a horizontal circle of radius 0.600 meters. The ball makes 2.00 revolutions per second, i.e., t equals 0.500 seconds, as in example 5.8, ignore the string's mass. So they want me to estimate the force a person must exert. So I'm going to say F sub C, meaning centripetal force, is equal to the question mark. We know that the mass is equal to 0.150 kilograms, and we know that the radius, which I've been using a capital R for just for convenience, is 0.600 m, or meters in other words. And it said the ball makes 2.00 revolutions per second. So 2.00 revolutions per second, remember, is the same thing as 2.00 cycles per second, which is the same thing as 2.00 hertz. Once you got to that point, you realize that that is the frequency F. And now I'm going to write down solution. The centripetal acceleration, a sub c, is either omega squared r or it's v squared over r. We have the summation, oops, we have the summation of the forces, in this case, in the radial direction, is equal to mass times acceleration in the radial direction. And in this case, the acceleration is going to be radial. We also have that frequency is 1 over the period, which is sort of what they use because they told us parentheses t is equal to 0.500 seconds. You can realize that if you take f as equal to 1 over t, then t is equal to 1 over f. And of course, if f is 2, 1 over 2 is 1 half. Therefore, you get the 0.500, which is what we're told and what I just wrote down. So now we can go about calculating it. But to do so, I need to draw a little picture. So we're going to draw the circular orbit like that, roughly. It looks like an ellipse because I've tried to draw a three-dimensional circle in two-dimensional paper. But really what's going to happen is you're holding it such that your hand maybe is holding up like this. So maybe these are your fingers and you're holding the string, and then the string is going to be tilted at some angle phi above horizontal, and then the ball on the end, which has a mass m, is going to be like that. So that's the actual drawing. As a first order approximation, we can ignore the fact that the string is going to dip, and in fact, if you go fast enough, of course, you can't go too fast. If you go too fast, the string's going to break because a string has a finite length, finite strength. But if you go fast enough, the faster you go, the smaller and smaller that angle will become, and therefore we can assume sort of a very small angle, and then that makes some simplification. So let me draw a free body diagram at an instant, at specifically this instant in time. So you see where the ball is right now. What we're doing is imagining the free body diagram. Uh, for that, I'm going to call the positive x direction pointing to the right and the positive y direction pointing up. And I'm going to put the ball dead center on the origin. And then what we realize is that in reality, the tension is up at that angle phi. Okay, so that would be our tension force. But that would suggest that the tension force has a component, and I shouldn't have used green there. I did that yesterday too, like a dummy. I'm going to use a color other than green or red because we're using green for the positive coordinate direction and red for the negative coordinate direction. So I'll just use a blue like this, and that's our tension. And again, that's up an angle phi. Now, if we were to break that up into components, what we would see is it has a positive x component, that's t cosine phi, and it also has a positive y component, that's t sine phi. If we assume phi is close to zero, then sine phi is approximately equal to zero. It's actually, as a first order approximation, the sine of phi is basically a phi, and then plus, yeah, it should be actually minus 1/3 phi cubed, so on and so forth. But we're going to assume that that's very small. Now, we also have to realize that the acceleration of the ball is a sub c, and that points to the right. Notice again, I put the acceleration adjacent to the free body diagram because in physics, when we make a free body diagram, we have a free body diagram for the forces, and we don't put the acceleration on the same graph as the forces because that might trick you into trying to add an acceleration to a force, and they can't be added. They're different quantities with different units. So we just put it off to the side and use that. Now, there's also another force acting here, and that force is the weight of the ball. So that force is m times g. So if we ignore or if we assume the phi is small, then we can proceed as follows. Assuming phi is approximately 0, then we get the summation of the forces in the radial direction is equal to mass times acceleration in the radial direction. And we see that we can ignore that little t sign phi. And by ignoring that, we realize that's the thing that has to hold up the weight. So we're also ignoring the weight of it. Okay. So all we're looking at now is that the tension in the string, instead of it being t cosine phi, since phi is approximately 0, the cosine of 0 is 1, so it's just t. So we have, in this case, t as the only force capable of supplying the actual centripetal force, and that is given by the mass times v squared over r. So that means the force centripetal is equal to the tension, which equals the m times v squared over r. So I'm going to put in the m, that's 0.150 kilograms. I'm going to put in the v, but of course we've got to work out what the v is. And of course, v is equal to uh, 2 pi r over t, but we also might try omega squared r. Yeah, I think I should try omega squared. Well, never mind. I showed you omega squared r a second ago, so I'll just use this one instead. So this is going to be 2 times pi times the radius, which is 0.600 meters, divided by the period, which is 0.500 seconds, and that gives me the velocity is 2 times 3.14159 times uh ooh, times zero point 0.6, and then I'm going to divide by zero point 0.5, and that gives me a velocity of 7.540 meters per second. So now I'm going to put that in here, 7.540 meters per second for velocity. Of course, that's got to be squared. And then I'm going to divide it by the radius, which is 0.600 meters. And you can see the meters per second when that's squared multiplied by the kilograms is going to give kilograms meter squared per second squared. But then we're going to divide by a meter, so that's going to make it, instead of kilograms meter squared per second squared, it's going to give us kilograms meters per second squared, which is the Newton. So that's the unit we're looking for. So now I'm going to take this 7.540 and I'm going to square it. And then I'm going to multiply that by 0.150. And then I'm going to divide that by zero point 0.6. And that's going to give me 14.21. And this extra zero was not a sig fig, so that's 14.21 newtons. Therefore, the centripetal force is on the order of 14.21 newtons. I don't know why I started writing meters per second there like a crackhead, but that's me. So, all right. So that's the answer we're shooting for. That gives us roughly the centripetal force has to be supplied. So, for instance, if you bought fishing string to try to do this, what you'd want to use is like a 16 Newton test. Now, I'm used to buying fishing string and it's written in pounds, so you'd have to convert that. But remember that 1 pound is about 4.45 newtons. So if you divide 1 by 4.45, that's what how many newtons you'd have. But anyways, you buy that type of string that can sustain that force, and then it won't break when you're doing this. Now, in reality, the problem here is we actually didn't solve the problem. We just gave a rough estimate of it. So now we should go back and say, let's go ahead and do the whole problem instead of just estimating. Let's figure out what it should be. So I'm going to use that same free body diagram, and I'm going to write here and just say extra. Your book does something like this as well. Where they take and he explains in sentence form how you'd go about solving this problem. I'm just going to go ahead and take the free body diagram and solve it instead of just telling you about it. So the summation of the forces in the y direction equals mass times acceleration in the y direction. That's going to be one of the equations of motion. That's what we call Newton's second law. It's also what you call the x of t or the r of t or the y of t as well as another equation of motion in some sense because it's actually the solution of the equation of motion. But in this case, we have an object that's rotating like or revolving like this around your hand. And in principle, if you've got it balanced right and you're spinning it at just the right rate, then the height of the ball isn't going to change. That means the y coordinate's not going to change, and therefore the acceleration in the y direction is equal to zero. Now we can use that. We can say the summation of forces in the y direction is equal to zero, and we see those forces are, strictly speaking, just t sine phi, which points upward. And then we have to add to it the weight, which points downward. So that's plus a negative, but we're just going to say minus m times g, and that's equal to zero. And from that, we can reach the conclusion that t times the sine of phi is equal to mg. And I'm going to call that equation one. We're going to be using that in a little bit. Okay. Now, the other thing is we take the summation of the forces in the x direction, or excuse me, we'll say in the radial direction, which is the same thing as the x direction. It's just a snapshot of it. The summation of forces in the radial direction is equal to mass times acceleration in the radial direction. And we know exactly what the acceleration is. We've, calculated that and everything. So now we just have to realize the only force acting here is in the x direction is t cosine phi. So I've got t cosine phi is equal to m v squared over r. That's going to be equation two there. So if we wish, we can go ahead and solve one for the tension T to get T is equal to mg over sine phi. Okay. And then I'll call this 1 prime since it's equivalent to equation 1, but it's just altered a little bit. Now we plug 1 prime into 2. And when we do this, we get mg over sine phi is equal to m v squared over r. Oops, left off something. Hold on a second. I was looking right at it. I don't know why I left it off. So I just replaced the t in t cosine phi with mg over cosine, mg over sine phi. Now I've still got to multiply by the cosine phi, and I was looking right at it and then didn't do it. But here it is, cosine phi right there. That's equal to mv squared over r. Now you can see that the m on both sides means we can divide both sides by m, and that means the result is independent of m. And not only that, we can see that cosine over sine is 1 over tangent. So we get 1 over tangent phi is equal to, uh, I'm going to pull the g to the other side. So that'd be v squared over gr, or more specifically, tangent of phi is equal to gr over v squared, and therefore we could say phi, the angle that it is actually wilting or sinking by, that angle phi is given by the inverse tangent of gr over v squared. So now that we have the phi, we could in principle make a triangle associated with that. Specifically, that triangle would look like this. Here's the angle phi. Tangent is opposite over adjacent. Obviously, tangent phi equals gr over v squared could mean that this side is gr and this side is v squared. So Christine's asking about the practice tests, why they close at a certain date. So what I leave open is the individual practice chapter practices, but the practice test I put up for you guys to prepare for the practice for the actual test. So when I've done that, I've found that a small percentage of the class, actually a pretty significant percentage of the class, chooses not to do it. It's completely the most absurd thing I've ever seen in my life. College students who are, mature enough to be adults at that point are choosing not to take a practice test when that is not the norm for colleges. Colleges and universities are not a place that they normally give a lot of practice tests for. They just show you the material and let you do your best. So for some reason, students still don't take the practice test. So what I tried to do is incentivize them taking the practice test by giving them extra credit. But once I do that, then I can't give them extra credit for taking it after the test is done. So that's why the practice tests disappear. And there's no real easy way for me to make it available again without messing up the grades on that and just having a nasty grade book. So that's what I do. But you're always allowed to do the individual practice for the chapters, which is in the section above practice tests. Hopefully that addresses it. But it's kind of neat with this one when we actually worked out the extra, we still get the same formula mv squared over r, but in this case, the mv squared over r is going to have a slightly different v. So I should write that as a note. Note v in this case is different. Okay. So that's the key thing, and that's going to give us a little bit of a correction. Uh, we could actually figure out what it is because v would be 2 pi times zero point 0.6 times cosine of phi. But in order to do that, I'd first have to solve for phi, which involves that v again. So it's a little bit circular, but what you could do is you could plug in the v for being 7.540 in this quantity to figure out what phi is. And then using that phi, we could use the fact that the radius is zero point 0.6 times the cosine of that phi. And then we could go back and calculate the velocity again using 2 pi times zero point 0.6 times cosine phi as the distance traveled and then divide that by the period, and that would give us a slightly different velocity. Then we could plug that velocity in mv squared over r, and that would give us another approximation of the actual centripetal force. But at that point, it's partially incorrect because we used a phi that was based on a v that wasn't right. So the next thing you do is then say, okay, now that I know what that force is, or what that velocity is, let me use that velocity to calculate the new phi, do the phi again, and then do it all over again. And basically, you can keep doing that until you get as many decimal places holding steady that you want, and that would give you the most precise answer. So that's certainly a fun, worthwhile. I say fun; it would be fun for me, but it's certainly a worthwhile thing to do, and you can do that as an extra credit if you'd like. I'll try to see if I can word it some way that y'all can try it as an extra credit. But anyways, I've spoken what you have to do, so hopefully that's enough. You have any questions on that one, Christine? Again, Christine's the only one here. So let's go to example 512. Example 512 says this is revolving ball parenthesis vertical circle. A 0.150 kilogram ball on the end of a 1.10 meter long cord of negligible mass is swung in a vertical circle. A, determine the minimum speed the ball must have at the top of its arc so that the ball continues moving in a circle. And then B, calculate the tension in the cord at the bottom of the arc, assuming the ball is moving at twice the speed from part A. So that's what we're trying to solve here. What we're given is that the mass is equal to 0.150 kilograms, which we can see is the same mass that we used before. Of course, we have a radius that's different this time. It's 1.10 meters. And what we want to say in part A is V min equals question mark at top, such that, well, I won't say such that, it's just V min, and I'll have to explain to you what we mean by V min. And then for part B, if V is equal to 2 V min, then what is T? So that's what we're trying to answer in part B. Let me cheat a little bit and let this computer program make a circle better than I can make. Ooh, isn't that perfect? Okay, and now I'm going to assume that the center of this circle is roughly right about here. That looks pretty good, I'm thinking. Okay, and I'm going to consider the mass up at the top, which would be right about here. And there is the mass m, and that mass m actually has a velocity v like this. Now, what I'm looking for is the minimum velocity. So what's going to happen is if you spin it just right, and you've probably done this with a bucket of sand or a bucket of water on the beach or something like that, or at a pool, if you spin it just right, you can go fast enough that the force of gravity is exactly the force required to keep the circle or the water or the sand in the bucket going in a circular orbit. If you do that, then that's the minimum speed. Because if it goes slower than that, then the centripetal force is actually bigger than mg. So it's going to use all of mg to pull the stuff down, and it still needs more to keep it in a circle. So that's what we mean by v min. To explain that, let me draw a free body diagram at the instant at the top of that. So in this case, I'm going to say the x direction is this way. And actually, I'm going to say the positive y direction is down, and you'll see why in a second. But here's the ball of mass m right here. Now, the forces acting on it are the force of gravity, which is the weight. So we've got mg, but we also have the tension in the string, T. And additionally, we know that the acceleration is a sub c equals v squared over r. So that's the actual acceleration we're going to have. Notice that's in my positive y direction. So I just write v squared over r in the summation of forces radial equals mass times acceleration in the radial direction. So now let me do that. So this is, by the way, at the top. So this is the free body diagram for at the top. Now I'm going to say the summation of the forces in the radial direction equals mass times acceleration in the radial direction, which in this diagram is clearly the y direction. But what we see is we have T plus mg is equal to mv squared over r. If we allow T to go to 0, then V goes to V min. So notice if I go slower and slower and slower, eventually I could get so slow that the force on the left-hand side is not as big as V squared over R, and then that's going to make the ball fall down. I need to avoid that. So the bare minimum speed I could go is the speed at which the entire mv squared over r is handled by the mg, and I don't need any tension in the string. So literally the string would just go slack if there was any less force. So that's what we're going to do. And now we say from this, therefore, mg is equal to mv squared over r, so that we realize, and this is min, by the way, so v min over r, we can see that the m's cancel out, and lo and behold, we get v min is equal to the square root of g times r. So that's what our minimum velocity is. I can go ahead and say a v min is equal to the square root of g times r, which is equal to the square root of 9.80 meters per second times the r, which is 1.10 meters, you see that when we multiply meters times meters per second, you get meters squared per second squared, and the square root of that is just meters per second, which is exactly what we want. So I take 9.80 times 1.1, and that gives me 10.78. Now I'm going to take the square root of that, and that gives me 7 root 22 over 10, which is super, super helpful. Uh, but it actually works out to 3.283. And we really only had 3 sig figs, so I underscore the 3, but that's 3.283 meters per second is equal to V min. So we've now solved part A, the minimum velocity that the ball can have to maintain the circular orbit at the top would be 3.283 meters per second. And of course, at that point, the tension in the string, it would become zero and the string would go slack if it was going any slower. Now for part B, we're going to assume that it's at the bottom. So I'm going to take and draw the ball at the bottom. This time the velocity is this way, and V is going to equal V times 2 times V min. And of course, we still have the 1.10 meters, but now I have a free body diagram for the top or for the bottom, and that's going to be like this. I don't need it quite as big, but in this case, I'm going to say this is the X direction, and I'm going to say this is the positive Y direction, and my mass is right here. I have that the tension in the string is pulling upward, and the mass or the weight, the force of gravity, is pulling downward, so that's mg. And we know that in order for this thing to maintain a circle, the acceleration has to be upward. Oops. The acceleration has to be upward because that's where the center of the circle is. So we'd say A sub C is equal to V squared over R, and it is pointing upward. So from that, we can now take the summation of the forces in the radial direction equals mass times acceleration in the radial direction. And this is going to give us T minus mg is equal to mv squared over r. And from that, we can see specifically they want to know what the tension is. So we can see that T is equal to M times G plus V squared over R. So that's the actual formula. T is equal to M times G plus V squared over R, like that. Now I can plug all this in, 0.150 meters per second, or excuse me, that's supposed to be kilograms. I was thinking of the velocity already. So 0.150 kilograms times 9.80 meters per second plus the velocity, which has to be twice Vn. If you multiply V min times 2, you get 6.567. So that's going to be 6.567 meters per second. That's got to be squared. And I'll just put a little note here. This is V equals 2 times V min. So that's where that came from. And then, of course, this is going to be divided by 1.10 meters. So as I compute this, I'm going to get 0.150 kilograms times 6.567 squared divided by 1.10 gives me 39.20. So this is going to be 9.80 meters per second plus 39.20 meters per second. So notice the centripetal acceleration is huge compared to the gravitational acceleration. It's just literally almost 4 times as much. So it actually might be 4 times as much. So the main thing that we see here is that the centripetal force required to keep it in a circle is way bigger than the weight. So uh, that's something that's kind of interesting, and in fact has some ramifications. If you saw 60 Minutes that happened in the 1980s, where a group of people tried to do a swing off of the Golden Gate Bridge, and the person didn't know any physics, so he just went to Home Depot and found some cable that was more than strong enough to hold up all the five people that would be tied on the end of it, and then they all jumped off. But because he didn't know physics, he didn't realize that the cable being, twice as strong as mg may or may not be good enough, and it turned out to not be good enough because the string busted before it even got maybe 30 degrees down, and the five people, one of which hit a boat, a couple other ones hit water, and many of them got severely injured, and he ended up going to prison for involuntary manslaughter. So it's very, very important to understand how these principles go. It's not always the mg's big enough. So now I'll take the 39.20 and I add to it 9.8. That gives me 49.00, and then I multiply that by 0.150, and that gives me 7.350 newtons. Uh, that seems right. 49 times 0.150. So this is 7.350 newtons is equal to the tension. And that is part B. But we could also write it this way just to remember that that is indeed the formula that we were able to work out. Any questions on that one? Okay. Now we're going to do a conical pendulum, and a conical pendulum is like a regular pendulum, but instead of the regular pendulum that goes back and forth like this, the conical pendulum goes in a circle like that. It's a flat circle like this, but we're going to use that to calculate specifically. It wants to know in what direction is the acceleration of the ball, what causes the acceleration, and then in part B it wants us to calculate the speed and the period in terms of L, theta, G, and M. So we're going to work this all symbolically, sort of like I was doing here with the M's and G's and V's and R's and stuff like that, only this time I don't have any numbers associated with it. So let's turn to example 513. Whoa. So example 513 gives me the following. It says a small ball of mass m suspended by a cord of length L revolves in a horizontal circle of radius r equals L sine theta, where theta is the angle the string makes with the vertical. See figure 520, which I'm going to draw. A, in what direction is the acceleration of the ball and what causes the acceleration? And then B, calculate the speed and period of the time required for one revolution of the ball in terms of L, theta, G, and M. So what they're meaning by this is they're meaning that we know, assume we know M, L, theta, and of course gravitational acceleration G. Now, when we work it out this way, what we've done is we've solved a problem. In fact, we've solved an infinity of problems because we've solved it for all the possible values of m, along with all the individual values of L for that M, and all the individual values of theta for that M, and all the individual values of G for that M in case we're studying separate planets. And then we can do it again for a various different L's with certain various M's and various thetas and various G's and so on and so forth. So you really get a whole infinity of problems that you've solved. What we want to know in A is which direction is the acceleration, and what causes it. And I mean, what causes that acceleration. And then in part B, we want to know V equals question mark and T equals question mark in terms of M, L, theta, and G. So let me draw the actual physical problem here. So we're going to imagine that we have a ceiling to which is attached this mass on the end of a string. So actually, I'm going to imagine it's tied right here. This dotted line is a vertical line, and what we're going to have is a string whose length is L, and this angle right here is theta. Now that L actually extends to the center of the ball, or we can just pretend like the ball is a point particle, so it's sort of the same thing. But either way, that's what we're doing. And then the actual path of the ball is that circular pattern right there. It looks like an ellipse again because we're trying to draw a circle from 3 dimensions and put it in 2 dimensions. But specifically, we can see that this distance from here to here is L sine theta, like that. And you could also see, for instance, that the distance from here to here would be L cosine theta, but we don't need that necessarily. So now I'm going to draw a free body diagram of this so we can make some sense of it. And again, I'm going to take just a snapshot of that instant in time. And here's my free body diagram. And the radial direction is what I'm going to call the positive X direction. And the positive Y direction is going to be up. And we have a mass, M, that is at the origin. And as you know, this is going to stay in a plane. So the acceleration in the Y direction is going to be zero again, like it has been for all these other things. But we do have something kind of odd. Specifically, we've got the tension T pointing at an angle theta, like that. Now, by necessity, that means that this angle over here is also theta. Okay, that is a fundamental geometric principle that we sort of expect you to know. And now I'm getting ready to teach it to you in case you don't know, because maybe you didn't have geometry. I know when I went to high school, I didn't get to go far enough to go to geometry because I was a deadbeat student. So uh, I'm trying to tell you I have empathy for you for that matter. So let me take a brief second over here to the left and tell you about something. So imagine two railroad tracks. Let's say we have a railroad track right here and we have another railroad track right here. Now, in geometry, if you make two lines that look parallel, they're not parallel unless we give you some indicator, like in the problem, it says these two lines are parallel. Or one of the things that geometry classes often do is they'll put an arrow on them in the same spot, just like this. And then those two arrows being on this graph or on this diagram tell you that these two lines are in fact parallel. And I've just made that the ugliest thing possible, but the main thing is you see that those two lines are now parallel. Now, the big deal is in geometry, we learn that when you have two lines and they have a another line that crosses it, traverses it, if you will, then this is a very big thing that we study. So specifically, if these two lines are parallel, then if a transverse line crosses two parallel lines, then alternate, then one alternate interior angles are equal and two corresponding, I sounded out coro instead of corresponding angles are equal. Now that means specifically once you learn what alternate interior angles are and corresponding angles are, that means that if the two railroad tracks are parallel and the rebar crosses it, then alternate interior angles are equal and corresponding angles are equal. But if the railroad track lines are not parallel, then those two are not equal. So let me show you what interior angles are. So specifically, this angle and this angle and this angle and this angle are all interior angles because they're in between the two railroad tracks. So this angle is interior, this angle is interior, this angle is interior, and this angle is interior. This angle is exterior, as is this angle, as is this angle, as is this angle. Okay. So when we say alternate interior angles, what we mean is two angles that are interior but are on alternate sides of the transverse line. So what we mean by that is I'm going to use different colors to indicate equal angles. So this blue and this blue are both equal angles because they're alternate interior angles. Notice they're both interior. So that makes them interior angles, but they're on alternate sides of the transverse line, so that makes them alternate interior angles. So those are equal. Additionally, this angle and this angle are alternate interior angles, so those two are equal. Okay. Now, let me show you one more scenario. Maybe I can do better with my little triangles this time. If I could just stop being so OCD about it. Now we've done alternate interior angles. Now let me show you what corresponding angles are. So the corresponding angles are angles that sort of meet the same criteria. So for instance, if you consider this angle right here, that angle would say, hey, my right hand border is a railroad track and my bottom border is the rebar that's laying on the railroad track. So if I find another angle that says that same thing, then that would be a corresponding angle. And you could see that that angle is in fact this angle. So those are corresponding angles. And these are alternate interior angles. Now there's other corresponding angles. For instance, this angle right here, that angle would say, hey, I'm bounded on the left by a railroad track and bounded on the bottom by rebar. So this angle could also make that claim. So that one's a corresponding angle as well. Additionally, this angle would say I'm bounded above by rebar and to the right by railroad track. So it corresponds to this angle. And I could also say that this angle right here is bounded above by rebar and on the left by a railroad track, and this angle matches the same thing. So those are all corresponding angles as well. Okay. Now, in addition to that, there's this other neat little thing. Basically, if you have two lines, don't matter what angle they cross at, then where they cross is called a vertex, and therefore vertical angles are also equal. So this angle right here is across a vertex from this angle. So these two are vertical angles. And that's the symbol for angle, by the way. And not only that, these two are also vertical angles. So doesn't need any extra rule. Whenever two rays cross each other like this, they make two sets of vertical angles, and vertical angles are equal. That's always the rule. There's no time at which vertical angles aren't equal, at least in flat space. Okay, so that's some of the geometry that you need to make some sense of this entire course. If you haven't had this geometry before, then hopefully this will help you. But that's also part of what I did when I used the incline plane with the snow skier and the incline plane with the Atwood machine and stuff like that. We had to work out complementary angles and all that sort of stuff too. So hopefully that helps you. Now, that is why, specifically, why this angle theta is the same as this angle, because this line is vertical, as is the y-axis. Since they're both vertical, they're parallel. Since they're parallel, this transverse has alternate interior angles theta and theta. So that's kind of helpful. Now, the other thing we have to realize is that the other force acting on this mass is the force of gravity, which acts downward, and that force is mg. Now, the force of tension is actually purple, specifically because it's not parallel to the x-axis or the y-axis. So I need to break it up into components parallel to the x-axis and y-axis, and obviously that would mean the y component is positive, and this would be given by t cosine theta, and the x component is also positive, and that would be given by t sine theta, like that. So I can now take the summation of the forces in the y direction equals mass times acceleration in the y direction. And again, this is acceleration in the y direction is equal to zero because the height of that mass is not changing, so the velocity is not changing, and since the velocity is not changing, the acceleration is zero. Oh, and I should put that the acceleration is a sub c equals v squared over r right there, and r is equal to L sine theta. Okay, so now I can write the summation of forces in the y direction equals mass times acceleration, and for that I basically get t cosine theta, which is the vertical upward force, minus mg, which is the vertical downward force, and I did minus because it's plus a negative, and that's equal to zero. So again, I get t is equal to mg over cosine theta, and I'll just call that equation 1, so that might come in handy. Now I'm going to take the summation of the forces in the radial direction is equal to mass times acceleration in the radial direction. And for this case, we see that the only force in the radial direction is t sine theta. So we get t sine theta is equal to mv squared over r, which again, we've figured out that r is L sine theta. So t is going to equal, or excuse me, t sine theta is going to equal mv squared over L sine theta, like that. And this is going to be equation 2. Okay. So now I can combine equation 1 and equation 2. And the way I'm going to do that is I'm going to take the t and plug that in from equation 1 into equation 2. So I'm going to get mg over cosine theta times sine theta is equal to mv squared over L sine theta, like that. You can see that the m's cancel out, and you can also see that v squared is equal to g times L times sine squared theta divided by cosine theta. So we can solve for v by taking the square root, and the square root would be the square root of gl sine squared theta over cosine theta, and that's our velocity that we're looking for. Notice it's a velocity. It only involves L, G, theta, and M, even though M didn't appear in it. So now this is part of B. I haven't explained A yet, but I'll get back to that. Now, in addition to that, we know the velocity is given by 2 pi r over the period. So velocity is equal to, let me write that in purple again. Velocity is equal to 2 pi r over the period, but the r is L sine theta, and therefore we can see that the t would be 2 pi L sine theta over v. So t is equal to 2 pi L sine theta. And then the v is in the bottom, so I'm going to flip that fraction over and I'm going to say it's times cosine theta over GL sine squared theta, like that. I'm going to pull that. I'm going to leave the 2 pi out in front, but I'm going to pull the L sine theta inside. And because of that, I'm going to get G L squared sine squared theta cosine theta over G L sine squared theta. And you can see that, in fact, the L squared is going to cancel out with the L down here. The G is going to cancel out with the G here. And the sine squared is going to cancel out with the sine squared here. So I can finally write that the T is actually quite simple. T is equal to 2 pi times the square root of L cosine theta over G. So that is also the answer for part B. Now, part A said, what is the direction of the acceleration? I think that's pretty obvious from my diagram, but the direction of the acceleration is this. So that's part A. Now we can also see from this diagram that T sine theta is the force that causes A sub C. So that's another part of answer A. So remember they said what direction is it and what causes it? So the tension in the string times the sine of theta is the force that actually causes the centripetal acceleration. And the centripetal acceleration points towards the center of that horizontal circle. Any questions on that? All right, your book at the bottom of page 130, or excuse me, top of page 130, gives you a problem solving for uniform circular motion. Highly recommend you read that. You'll see that it's pretty much consistent with the way I do things, but hopefully that works out. And now what we have to work on is banked curves. So we're looking at curves that are banked to basically allow a car to make a turn even when there's no friction force, for instance, in the snow and stuff like that. If you try to take a turn on a flat surface, what you're relying on is the friction between the tire and the road to allow the car to actually turn. And if you don't have any friction, like if you hit a patch of ice there, then what happens when you try to make that turn is you turn your steering wheel and you just go straight. So that's not very helpful. So what we're going to do is we're going to solve problem 514 for starters. So let's look at example 514. Example 514 says a 1,000 kilogram car rounds a curve on a horizontal flat road of radius 50 meters at a speed of 15 meters per second, which is about 54 kilometers per hour. Will the car follow the curve or will it skid? Assume A, the pavement is dry and the coefficient of static friction is 0.60. I'm going to add three, I'm going to make everything three sig figs. And then B, the pavement is icy and mu static is equal to 0.25. Again, I'm going to make that three sig figs as well. So for starters, I've got the M is equal to 1,000. And notice I put the decimal place there. So that makes it look as if it has four sig figs. That's what I'm pretending is I'm going to pretend the mass is known to four sig figs. I know that the radius is 50.0 meters. Again, I added the extra digit so that we have three sig figs. I know that the velocity is equal to 15.0 meters per second. Again, that's about 54 kilometers per hour. And I assumed one extra sig fig. A, will it skid if mu sub s is equal to 0.600, and that's the value for dry pavement, or B, will it, if mu static is equal to 0.250. So that's what we're working on here. Let me draw a free body diagram for the car. Now, really, it's a car, but we're going to pretend it's a point particle because that's what we have to do until we cover center of mass and torque. And what we have acting on the car is a vertical force. That's the normal force applied by the road. Of course, that's in the y direction, and it's positive. That's why I drew it green. And in fact, we also have the weight associated with the car, which is the force of gravity, and that is mg. Of course, the mass is just m. And of course, we're trying to make a turn, so we can sort of represent that by saying the road goes like this and like that. And the radius, of course, is 50 meters. But in order to make that turn, we actually have to have a friction force that is applied to it in this direction right here. So that's the static friction force. And of course, that's our x direction or our radial direction, either one. So with that, we can say the summation of the forces in the radial direction is equal to mass times acceleration in the radial direction. And we can also say the summation forces in the y direction equals mass times acceleration in the y direction. But again, we're going on a flat road, so the y coordinate is not going to change, and that means the acceleration in the y direction is 0. So in this case, I get specifically, and I never labeled Fn, that's the normal force, Fn right there. Okay, so I get Fn minus mg is equal to 0, and that tells us that the normal force is just the normal mg, and of course that's 1,000 times 9.8, so that gives me 9,800 newtons. That's what the normal force is, and that's what mg is. Now, that also allows me to calculate, because the static friction maximum, remember, static friction is less than or equal to mu static times the normal force, but the max occurs when it's mu static times the normal force. So that's going to be 0.600 times 9,800 newtons, and actually I'm going to write that below it. So I'm going to say F static for dry pavement is equal to 0.6 times 0.6 gives me 5.88, or 5,880. newtons is the dry pavement. Of course, F static max for what they call it, icy pavement, is equal to 0.250 times 9,800 newtons. So 9,800 times 0.25 gives me 2,450 newtons. So that's the two maximum frictions we can get in the dry case, which is part A, and in the icy case, which is part B. So what we got to figure out is what is the necessary friction force, i.e. the centripetal force. So using the summation of the forces in the radial direction, using the summation of forces in the radial direction equals mass times acceleration in the radial direction, and noting that the acceleration is a sub c and points to the right, which is our positive direction, our positive radial direction, then that means the friction static has got to equal mv squared over r. So let's calculate what the friction static has to be, which is also equal to the F centripetal. Okay, so we think the friction static force is hopefully going to be big enough to make it make the turn. So what we're really calculating is F sub c. So that's why I wrote that over there, is so you realize F sub c, the necessary centripetal force, really is the mv squared over r, and it may or may not be equal to F sub S. So I'm going to put that in parentheses just to remind you that really what we're calculating is the centripetal force, which equals mv squared over r. And we got to compare it to those two maximum friction forces to see if A or B allows a skid or not. So with that in mind, I'm going to go ahead and say that and I don't know why I switched to green, but we're going to go with it. So the mass is 1,000 kilograms. The velocity is 15.0 meters per second, and that's got to be squared. And then the radius is 50.0 meters. So if I take 1,000 times 15 squared, and then I divide that by 50, I get 4,500 newtons with one extra digit, so it's 4.50 times 10 to the third is really what it is. And therefore, for part A, since F static max equals 5,880 newtons for dry pavement, and F centripetal is equal to 4,500 newtons, we see that the car does not skid. So our answer for part A is does not skid. For part B, since Fs max is equal to 2,450 newtons for icy pavement, and Fs max is less than Fc, we see that the car will skid. So that's the answer for part B. Any questions on that? All right. Now I'm going to do a derivation of what angle at which you wish to tilt a road so that you don't have to use friction to round the curve. I will remind you that when you do that, if you actually tilt the road at an angle so that friction is not required, if you then hit that road on a frictionless surface, meaning when it's snowy and icy or something like that, and you go slower than the posted speed limit, then you'll actually slide down the incline, which, if you've ever seen exit ramps or on ramps to interstates, they're often a big hole down there for you to fall in, or even a pond or something, a wastewater retention pond. So that's something to keep in mind. But that brings us to example 516 banking angle, or excuse me, 515 banking angle. So let's say example 515 banking angle. They say for a car traveling with speed v around a curve of radius r, I'm going to use big R instead of little r, determine a formula for the angle at which a road should be banked so that no friction is required. And that's part A. And then part B, they say, what is the angle for a road which has a curve of radius 50 meters with a design speed of 50 kilometers per hour? So B, phi equals question mark for V equals 50 kilometers per hour, which I'm going to call 50.0 kilometers per hour. And for R equals 50.0 meters. Again, I'm adding extra sig fig, and we'll work out that. So first off, let me draw the curve. So we might imagine the road is banked at this angle, and we're going to call that angle phi. And in fact, what it looks like is a car like this, headlight, headlight, maybe this is a Jeep, like that. And that's what's going on. Of course, it's a turn. So, and we know what the radius of the turn is. Now, again, I'm going to draw a free body diagram at that point again. But as I've been warning you guys, there is one case where you're using an inclined plane that is not very conducive to using a tilted coordinate system. This is that example. So when you're trying to calculate what angle to bank a curve, it's not good to use a tilted coordinate system. You can still use it. It's just going to be a nightmare to work it out. So I'm going to not use a tilted coordinate system. I'm going to use a horizontal coordinate system, which has the normal x direction to the left and the normal y direction upward, like this. But the big caveat is that we still have the road tilted at the angle phi. So there's the phi right there. And what we have is treating the car as if it's a point particle of mass m. What we see is we have a normal force that is not, it's not parallel to the y-axis or the x-axis. In fact, it's perpendicular to the road surface. So you can see, for instance, that this angle right here is theta. And because this is horizontal and this is horizontal, that means these two lines are parallel and this is a transverse line. That means that this angle right here is also theta. And now if you realize that this angle from here to here, this is the roadbed, and this is perpendicular to the roadbed. So this whole angle right here is 90 degrees. And if you rotated this by theta degrees and took this with it, it would rotate the same way. So hopefully you can see that this angle is also theta. So I'm going to go ahead and put that in there as well. Basically, what you can do is realize that this angle, let me use the laser pointer again. This angle and this angle, since that's 90 degrees, this angle and this angle are complementary. So if this was 30, for instance, then this angle would be 60. But this angle and this angle are also complementary. So if this angle is 60, then this angle would be 30, which was the original angle here. So that's why that's that angle there. And to make sense of it, I've got to break this down into components parallel to the X and Y axes. So I'm going to have a normal force component in the Y direction that is Fn cosine theta. And then in the X direction, it is Fn sine theta. And then in addition to that, we have the force of gravity, which acts downward, and that's the mg. Now, in this case, we're not going to have any friction. We're trying to design this road such that it's banked high enough that the Fn sine theta supplies the necessary acceleration. And by the way, the necessary acceleration is a sub c equals v squared over r, and it should go over to that way. So now I'm going to go ahead and say the summation of the forces in the y direction is equal to mass times acceleration in the y direction. Now, this car, we're imagining it's going around a bank curve, but we're not imagining them switching lanes or anything, so it shouldn't go up nor down, and therefore the y coordinate is not changing. The y coordinate not changing means the velocity in the y direction is zero, and the y coordinate or the velocity in the y direction being zero and then still zero means the acceleration in the y direction is equal to zero. So I'm writing it like that. That gives us specifically that Fn cosine theta minus mg is equal to zero. Therefore, we can say that the normal force is equal to mg over cosine theta, and I'm going to call that equation 1. So that looks familiar. We've gotten a result like that before, but specifically, we're now going to use that for our normal force. Uh, Now, with that normal force, we can combine that with sine theta, for instance, to get the force in the x direction. But that allows us to use now Newton's second law for the radial direction. The summation forces in the radial direction is equal to mass times acceleration in the radial direction. Again, looking at it at a split second in time, the summation of the forces gives us that the only force acting in the radial direction is Fn sine theta, and that's got to equal mv squared over r. And now that's equation 2. So plug 1 into 2 yields the following: mg over cosine theta times the sine of theta is equal to mv squared over r. And you can see again the m cancels out, which is great because if it depended on m, then we'd have a different speed for Mack trucks than we do for regular cars, and even a smaller speed for Cooper Minis and stuff like that. So luckily we don't have that, but we do know that sine over cosine is tangent, so we could write this as g tangent theta is equal to v squared over r. And of course, that allows us to say that theta is equal to the tangent inverse of v squared over gr. Notice that's the exact inverse of what we got earlier when we were doing the mass over our head spinning. We ended up getting the angle phi was the inverse tangent of gr over v squared instead of v squared over gr. So that's kind of neat. You can probably figure out why that is related that way. But now we have the actual expression for the tilting of the angle. And I don't know why I switched to theta all of a sudden instead of uh, phi, but let me go ahead and fix that. I'm sorry for that. I don't know why I switched to phi. I do like writing phi better, so I suspect it was something like that, and then I just forgot. So I'm going to call it theta, and then that fixes everything. I've gotten rid of all. Oop, nope. I got to change it up here too. So theta is that. That's our answer for part A. Circle that or box that off in red. That's our answer for part A. Now for part B, they want us to calculate what that angle is. Of course, I've made the phi over here too, so I've got to change that to theta. So now for part B, I say theta is equal to the tangent inverse of V. That's going to be 50.0 kilometers per hour times 1 meter per second per 3.6 kilometers per hour. That's the conversion factor. So I'm going to square that and divide that by 9.80 meters per second times 50.0 meters. And you can see that the units cancel out to give me nothing. So 50 divided by 3.6 gives me 13.89 meters per second. Now I got to square that. So that's 192.9 is what 50 divided by 3.6 is squared. Now I'm going to divide that quantity by parentheses 9.8 times 50, close parentheses, and that gives me the inverse tangent of 0.3937, and that's no units. So we get that theta is equal to the inverse tangent of that. So I'm going to say shift tangent inverse shift answer, and that gives me 21.49 degrees, which is about 22 degrees, which is what your book calls it. Any questions on that, Christine? I'm going to skip over the non not because it's being skipped for the subsection or anything. It's just a fairly straightforward example. Basically, when you have an acceleration, you have the acceleration that happens if you're driving in a circle in your car in a parking lot. If you keep your steering wheel locked in exactly that angle so that the car completely repeats the circle, and that's not necessarily a trivial thing to figure out, by the way, but either way, if you keep it in that main circle and all you do is hit the accelerator to speed up or you hit the brake to slow down, then that's a tangential acceleration. And then the acceleration that keeps you going in the circle is a radial acceleration. So the big thing to understand from all this, and I'll put the line right here to break it up, that oops, that A total is equal to A tangential, which is a vector quantity, and that would be tangential to the circle, plus A radial, which is also a vector quantity, but that would be radially towards the center. Or if you're actually allowing yourself to drift out, it would be radially outward. But the main thing is that the magnitude of A total would equal the square root of A tangent squared plus A radial squared, like that. That's the only thing you really need from that section. And you can see they worked one example, example 516, and that's it. That's fairly trivial. So I'm skipping over that so we can jump into the next part, which is air drag. And it's a pretty straightforward derivation, and I've already hinted to you guys on this one. We've told you that the drag force or air resistance is given by F drag is equal to, uh, I wrote a P there somehow. I don't know how I did that. F drag is equal to some constant times V, or F drag is equal to some constant times V squared. And those are the two choices. But normally the V squared happens when the fluid is super, super thick or when the velocity is super, super high. So it's probably a little more reasonable when you're talking about cars going, 50, 60 miles per hour. It's better to say that the F drag force is B times some velocity squared. And as I said, that B is directly related to the viscosity. So a higher viscosity makes a higher B. And it's also directly proportional to the cross-sectional area. And in that case, a high cross-sectional area, like me holding my arms out extended like that, makes a big area. That would make B large. But if I dove head first, then my cross-sectional area is just sort of what I look like from above, and that would make B small. We're going to examine just the case of BV. So let's imagine an object that's in fall, not free fall anymore because we have air resistance on it. So what we have here is a mass M. It has acting on it a force mg, and it also has acting on it a drag force. And actually, I should really have made that green because I'm going to point down as the positive direction. So I'm going to say this force is the force pulling down on it. But in addition to that, we're going to have a drag force FD, which equals B times V. Now, since it's B times V, as this mg is bigger than the drag force, then it's going to speed up and speed up and speed up. Each time it speeds up, then the drag force gets bigger and bigger and bigger. Eventually, what's going to happen is the drag force gets as big as the weight, and when that happens, the sum of the two forces is equal to zero. And Newton's second law says the summation of forces in the y direction is equal to mass times acceleration. But if mg minus bv is zero, then the acceleration's got to be zero, and that happens when the velocity is what we call the terminal velocity. So that's really what's going on here. So let's go ahead and write out the summation of the forces in the y direction equals mass times acceleration in the y direction. And what I'm drawing here is the y direction pointing down. So with that in mind, I get mg minus b times v is equal to m times a, but more specifically, m times a is actually dv over dt. So I will say mg minus bv is equal to m dv dt. Now, with that in mind, we can solve this differential equation. It's what we call a separable differential equation because we can basically get the parts that are dependent on dv or that are dependent on v. We can get those on the same side of the equation with the dv, and then the anything else we can put with the dt, and there's no t in it, so that's okay. So what we're going to do instead is we're going to go ahead and work this out. So what I'm going to do is divide both sides by mg. Let me see if I want to divide both sides by mg. No, I think I'll divide both sides by m. So I'm going to take both sides and divide it by m. And when I do that, I get g minus b over m times v is equal to dv dt. Now I can write this as multiplying both sides by dt. I'm going to say times dt times dt. And then I'm also going to divide both sides by g minus b over m times v by g minus b over m times v. And when I do that, I end up getting, in this case, the left-hand side just becomes dt, but the right-hand side becomes dv over g minus b over m times v. So that's a separable differential equation. What I'm going to do is integrate both sides, so I get the integral of dt is equal to the integral of dv over g minus b over m times v. Now I'm going to integrate from t equals 0 to some arbitrary time t. Mathematicians don't like us doing that, using the integration variable as the limit of integration, but we're going to do it. Okay. And I'm going to integrate from v equals 0 to v of t specifically. To do this, I'm going to say let u equal g minus b over m, like that, times v. therefore du is negative b over m dv. So if I have a negative b over m in front of the dv, then I have the equivalent of du. So what I'm going to do is multiply both sides of the equation by negative b over m, like that. Now that I've done that, I've got negative b over m times the integral dt from t equals 0 to t. And on the right hand side, I have the integral of du over u, because remember that negative b over m times dv gave me du. So this is going to be du over u, and that's going to be from v equals 0 to v of t. In other words, I didn't change the limits of integration to the new variable, but we know that the integral of dt is just t, and then I evaluated at t and 0, that'd be t minus 0, so I get negative b over m times t for the left-hand side. That's even after evaluating it at the range of integration, so taking t and then taking the case of t equals 0. The right-hand side becomes the natural log of u, and that's evaluated at v equals 0 and v of t. So in this case, I get g minus b over m times v, and I have to evaluate that at v equals 0 and v of t. So I get negative b over m t is equal to the natural log, and now I'm going to say it's g minus b over m times v of t over, remember subtraction, the ln of a minus the ln of b is the same thing as the ln of a over b. So that's what I'm using here. And when I evaluate v at v equals 0, then the g minus b over m times v just becomes g, like that. So now I can see that negative b over m times t is equal to the natural log, and now I'm going to distribute that g, and I get 1 minus b over mg times v of t, like that. Now I can raise the left hand, I can raise e to the left hand side's power, and I can raise e to the right hand side's power and set them equal to each other. And when I do that, I get e to the negative b over m times t is equal to, now remember, y equals log base b of x implies x is equal to b to the y power. So if you look at that, you see that when I raise the logarithm, or when I raise e, the base, to the logarithm power, then the argument is just all I get. So the e cancels out with the ln and gives me 1 minus b over mg times v of t, like that. I'm trying to solve for v of t. So what that gives me is negative b over mg times v of t is equal to 1 minus e to the negative b over m times t. This is all differential equations and algebra. It's pretty straightforward stuff, but if you can't remember it, that's not a big deal. We're going to get a result, and that's the most important part. But that it should be a future goal is for you to make sense of it. Now what I'm going to do is multiply both sides by negative b over mg, and when I do that, I'm going to get or excuse me, I'm going to multiply both sides by negative mg over b. So let me go ahead and write that. Multiply this by negative mg over b times negative mg over b, like that. And now from this, I get v of t is equal to negative mg over b times 1 minus e to the negative b over m times t. So we're pretty close there. And I can go ahead and change the order of this. I don't know why I got a minus now. Let's see here. That is right there. Oh, I remember. Sorry about that. When I pulled the B over mg times v of 2 to the left, that should have made this a positive. So everybody make sure you, uh, oops, everybody make sure you pay attention to that. Uh, this right here is supposed to be positive, not negative, and that means this right here is supposed to be positive, not negative. So now I can finally say that V of t is equal to mg over b times 1 minus e to the negative b over m times t. Now, if you wanted to actually make a graph of this, what you would see is that this graph as a function of time with velocity here is asymptotically approaching a very specific velocity, specifically the velocity of mg over b equals v. That is, specifically speaking, the terminal velocity, but the curve for this is an exponential growth asymptotically approaching this like that. So what that tells us is that one, that is the equation for a object falling with air drag and therefore the drag force acting on it. And it also tells us that V terminal is equal to mg over b, which is obviously exactly what I said when I said mg equals bv implies terminal velocity. You see that solving for v, you get mg over b. So that is actually the terminal velocity. V terminal is equal to mg over b. So that's another answer that's important. And that's it. We've now finished chapter 5, and we only got 3 minutes left. So of course you're free to go. Uh, if you have any questions, I'll wait as long as you have, and I'll wait for anybody else. Christine, do you have any questions? Actually, I don't even think Christine's here anymore. Let's check. Nope, it's only me. So that's it. Hope everybody finds this helpful. I did recopy that V terminal that's at the bottom, almost running out of the page. I copied that up into the blue box so that y'all would see that. And that's it. I'm going to go ahead and stop sharing and call it a day. Hope you all have a nice weekend. Thank you. Have a good day. Bye bye.